The size of the real numbers, the continuum, is denoted C. Is C the smallest infinity strictly larger than the natural numbers? This question, the continuum hypothesis, haunted mathematics for a century. George Cantor proved that the set of real numbers has a strictly greater cardinality than the set of natural numbers, Aleph-null. The critical gap lies between Aleph-null and the next smallest infinite cardinality, Aleph-one. If the continuum hypothesis holds, this gap is empty. C is exactly Aleph-one. If it fails, there exists an infinite subset of the real numbers that cannot be put into one-to-one correspondence with either the natural numbers or the entire set of real numbers. This intermediate cardinality would fundamentally alter our understanding of infinite sets, challenging the intuitive hierarchy of infinities. To rigorously address the continuum hypothesis, we must operate within Zermelo-Fraenkel Set Theory with the Axiom of Choice, known as ZFC. ZFC provides the foundational axioms for almost all modern mathematics, defining sets, membership, and operations like union and power set. The power set axiom states that for any set X, the collection of all its subsets, P of X, is also a set. Cantor's theorem proves that the cardinality of P of X is always strictly greater than the cardinality of X. Since the real numbers are equinumerous with the power set of the natural numbers, the continuum hypothesis asks whether the cardinality of P of omega is precisely Aleph-one, the second smallest infinite cardinal. ZFC is assumed to be consistent, meaning no contradiction can be derived from its axioms, a prerequisite for any independence proof.
The first major breakthrough came from Kurt Gödel in 1938. Gödel demonstrated that the continuum hypothesis cannot be disproven from the axioms of ZFC. He achieved this by constructing a specific inner model of ZFC called the constructible universe, denoted L. The universe L is the smallest transitive model of ZFC containing all the ordinals, built up iteratively using only definable operations. Gödel proved that if ZFC is consistent, then ZFC plus the continuum hypothesis is also consistent. Crucially, within the universe L, the axiom of constructibility, V equals L, holds true, and this axiom implies the continuum hypothesis. This established that CH is compatible with the standard axioms of set theory, showing that ZFC alone does not refute it. Proving that CH cannot be proven from ZFC required a radically new technique developed by Paul Cohen in 1963, the method of forcing. Forcing allows mathematicians to systematically extend a given model of set theory, M, to a larger model, Mg, by adding a generic set, G. This process preserves the ZFC axioms while controlling the cardinalities of the new sets introduced. Cohen used forcing to construct a model where the continuum hypothesis fails. Starting with a model M where CH holds, Cohen added a carefully chosen set of real numbers, increasing the cardinality of the continuum without collapsing the existing Aleph numbers. This technique fundamentally changed how independence results are established in set theory.
Cohen's specific forcing construction demonstrated that the cardinality of the continuum, C, could be made equal to Aleph-2, or even Aleph kappa for any regular cardinal kappa greater than Aleph-one. This construction showed that ZFC plus the negation of the continuum hypothesis is also consistent, provided ZFC itself is consistent. The key insight was controlling the size of the power set of the natural numbers independently of the definition of Aleph-one. Aleph-one remains the smallest uncountable cardinal in the extended model, but the new real numbers added by forcing ensure that the continuum C is strictly larger than Aleph-one. This established the existence of models where the continuum is demonstrably larger than the second smallest infinity. Combining Gödel's proof of consistency and Cohen's proof of consistency of the negation yields the definitive result. The continuum hypothesis is independent of ZFC. This means ZFC is insufficient to determine the truth value of CH. Within the framework of ZFC, CH is formally undecidable. This result is analogous to the independence of the parallel postulate in Euclidean geometry. Mathematicians can choose to work in ZFC plus CH or ZFC plus not CH, creating different, equally valid mathematical universes provided they are consistent. The independence does not imply that CH is meaningless, but rather that ZFC does not capture all necessary truths about infinite cardinalities. The independence of CH spurred the search for new axioms that might resolve the question. These potential axioms must be intuitively plausible and yield definitive results for undecidable statements. A primary candidate involves large cardinal axioms, which assert the existence of extremely large infinite cardinals whose properties imply the consistency of ZFC. While large cardinal axioms do not resolve CH directly, they often constrain the possible values of the continuum. For instance, the axiom of determinacy, incompatible with the full axiom of choice but consistent with Zermelo-Fraenkel, implies that the continuum C is Aleph-2, providing a concrete alternative to CH.
Current research focuses on finding a natural extension of ZFC that settles CH. Woodin proposed a program suggesting that certain strong large cardinal axioms might imply that the value of the continuum is fixed, potentially at Aleph-2. This approach seeks to identify axioms that maximize the structure and regularity of the set-theoretic universe, often referred to as maximizing determinacy. The ultimate goal is to find an axiom that mathematicians universally accept as true, much like the axiom of choice is accepted, thereby resolving the continuum hypothesis definitively. Until such an axiom is found, the independence result confirms that the structure of the infinite hierarchy remains open to axiomatic choice.